So it has a standard shape. They're packed together in like a lattice form. Good term to use is a lattice. And then what would you say about their motion? Okay, I'm going to say that so basically the idea of non-motion, no motion is only going to occur at something called absolute zero. Okay, so solids, are they at absolute zero? No, they actually are at room temperature, or maybe they get really, 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 really low, very cold like ice, but the molecules are still vibrating. They do not stop moving until you hit absolute zero. So they're still vibrating, they're just not flowing past each other. There's no translational movement, it's a vibration movement, okay? So that is one thing to note for a solid. So then liquids are going to have translational movements, they can move back and forth from each other, and then gases are definitely moving at the greatest speeds. They can move, they bounce off the sides of the containers. What do they cause? This is going to maybe later on in the videos. What do gases cause whenever they hit the side of the container? Pressure. So the pressure is mainly correlating with the presence of a gas. Liquids don't really cause a lot of pressure. Solids don't really cause a lot of pressures, but gases definitely cause different amounts of pressures. So phase diagram, what does it look like generically, Trinity?
It's kind of like a Y shape. Solids on one side and like gas on the bottom, and then liquid is right at the end.
So it kind of like looks like a Y shape like this, and it goes what?
It goes solid, liquid, gas.
And then what are the units for this axis, for the Y? What's the unit here? Okay, so I'm going to put pressure, and you're saying kilopascals. The pressure is in kilopascals. What's another unit that could go there? Did anybody see another unit of pressure? Say again? Say it again? A unit of pressure. You may have seen it in your reading guide. Millimeters. Okay, so I'm hearing millimeters of mercury and ATM, atmospheres. See another one? There's like 3 or 4. So torr is another one, and bars are another. So these are 5 units of pressure. Which unit of pressure have you ever heard of before? Which of these? Kilopascals, millimeters of mercury, atmospheres, torr, bars, or pressure, oh gosh, pounds per square inch. PSI. Have you heard of PSI? Maybe? Who's ever put a tire pressure reader into their tire gauge? Okay. Well, unfortunately, we have a disproportionate population of more guys have done that than gals. Gals, you should learn, first of all, learn how to change your tire. And learn how to check your tire gauge or check your tire pressure. Something you need to do. So it should not really on your bucket list. It's kind of like a necessity as a functioning human being, okay? Especially if you're going to be driving. But pressure or pounds per square inch is what we Americans use. These other people, like for the SI system, will be using these. Commonly, we will be using atmospheres because a lot of times we talk about the pressure of the atmosphere, so we talk about it in terms of atmospheres. Guess what atmospheric level we live at? Say 1 atmosphere. We live at this nice 1 atmosphere. If we lived on top of a mountain, like super, super, super high mountain, what do you think our atmospheric pressure would be? Let me tell you about atmospheric pressure. Here's us. I'm going to draw this picture. It's beautiful, by the way. This is the mountain. This is us. We're at 1 atmosphere. Pressure, P equals 1 atmosphere. What's causing that pressure? Right, all this air from here, from eternity, up here, all the way down, is causing all that pressure. So if we're up here with the birds, what do you think the pressure on the top up here would be? After a long, strenuous hike, we're up there. Less than 1, because all this pressure cumulatively makes 1 atmosphere. We're way up in the sky now. Let's go 0.5. Just make it quick and easy, right? So 0.5 atmospheres, and that's because there's less air up here, less layers and layers and layers of air molecules pressing down on us. So what are some conditions people experience when they get that high on a mountain? Yeah. They what? They have a hard time breathing. Well, because they're used to having, let's say we have this much air. 21% of that's oxygen, right? We inhale 21% oxygen. We exhale some carbon dioxide. We breathe it in, and we're feeling good. we get up there, it's a lot less dense. So here it might look like, here's my box of air, okay? I carry around a box of air with me at all times. It looks like this. It's pretty compact. I can't really make it compact, but there it is. Up here, what would it look like? Less condensed, less dense. So it might be like that. Okay? There's a lot more here for me to breathe in a given breath versus here. Now, under the ocean, here we go. Here's the ocean. I'll label it for you. And we're down here with our goggles on. Okay? And a little air tank, scuba diving. Bubble, bubble, bubble. Okay? So tell me about the pressure there. Yeah. I'm guessing you're right, Niall. I have no reason not to believe you. But I'm going to go with more, just more. So give me something. Give me a pressure that could occur down here. Sure, 2 atmospheres, 1.5 atmospheres, whatever you want to say. So give me a characteristic about being down below the ocean. I know it's hard to breathe because there's water. Okay? Tell me something more. What do you feel when you hit the bottom of a pool? Okay, the bottom of the pool. You hit the bottom of the pool, you feel the bottom of the pool. What are you saying? Your ears like hurt. Right, so there's a lot of pressure pushing on your eardrums. And that's abnormal, so it starts to hurt, and it actually, sometimes can be dangerous. But the pressure, you have to pop it and try to exchange the pressure and come to equilibrium inside your head and outside of your head. Okay, so that's because there's not only air, but then there's water, which is, of course, even more dense. Okay, so that's going to be our differences in pressure. So we're talking about atmospheric pressure a lot more today. But the only reason I brought that up is because I want you to know some units of pressure. How about across this axis? Temperature, right. So the phase diagram has pressure versus temperature. That's different than the next thing you talked about, which was the heat curve. So, James, feeling it, what's the heat curve look like? Okay, like this, so a curve that looks like a staircase? I know. Most of the time we're not creative, but this is creative. They call this a heat curve. That's not a curve, but we're going with it here, okay? So what are the units of on the axes here? Avery, give me one of them. Which one? So that y-axis is temperature. That's probably going to be in degrees Celsius or Kelvin. There's 2 different units of temperature. And then down here, time. And time can be here, or it can say heat added. Okay, so those are going to be 2 different terminologies that we'll use, and I'll talk about why later. But that's our heat curve. So can anybody take a guess what a cool curve looks like? So when you say opposite, it's going to start at the top temperature and cool down. Okay, so a heat curve is going to heat up, so from cold to warm, and a cool curve is going to go like this. Okay, so this one's going to cool down, and this one's going to heat up. Okay, same units, time, temperature versus time, or temperature versus heat added. So we're going to dive into those a little bit more. But before we get into this, let's explore pressure a little bit more. Okay, here's what I need you guys to do. Not that. Yes, this. Okay, you can do it. We're going to deal with cans. We're going to make so we're going to put a little bit of water inside of a can, and we're going to boil it. That means heat it up. Then we're going to put the can upside down inside of a beaker of cold water, an ice bath is what we call it. So we're going to fill up the beaker about halfway with water, about halfway with ice, and then we're going to go for it. And I want you guys to make observations. Tell me what you see. You need just a half sheet of paper, some scratch paper. You're going to write down some observations on. Read this in depth. Get into groups of 3. This is done in less than 10 minutes, okay? Less than 10 minutes, groups of 3. Go. Call this a you can do it. All right, guys, the instructions are on the board. You need to get the hot plate going, not with the beaker, but with the can. Read the instructions on the board before you begin. Small amount is like less than 2 milliliters. Small amount. And you guys can get a little ice. Some look at the can doing, some look at the beaker. You guys are working
Good, it's one thing. Is your hot plate on full heat? Yay or nay? Yay. Hot plates on full heat. The stir bar should not be on stir. No stir, only heat. So your hot plate is heating up the water. Yes? Your hot plate is heating up the water. You have a cold bath that's to the side. The beaker is mostly full because you only need a small gap at the top. You're not done yet. I'll tell you when you're done. You're not close, so restart. Okay, so what you're going to do is you're going to wait for your small amount of water to boil. What you'll notice is that the steam will start to come out of the opening of the can. You'll actually hear it go inside, so that you'll actually know it's boiling. So you guys need to get reset, like now. So what you're going to do after I tell you, like, you're going to do a lot of steps. I want you to have a good there the first run. Just call me over. You're going to take your, these guys, keep your tongs, and you're going to grab it. 1 second. You're going to grab it, and you're going to flip it upside down immediately into the cold bath. So like this picture right here, you guys see? You guys see? Okay, some of their smoke's not actually coming from there. Is it popping? Okay. So it's okay. Do not go prematurely. I'm going to give it another second. Give it another minute maybe. It's not all going to boil out, but you can only do one can at a time into the ice bath, and then you're also going to explain the packing. Okay? Give it a second. I'm going to go I want it to be like vicious pocket, okay? I want it to be vicious pocket. No, I do not. This is not vicious.
Have you ever boiled water?
Guys, everybody give it about 30 more seconds. I want it to be really hot. So talk about science and life. All right, guys. I think you're close to ready. So again, let me just tell you here. One group at a time is going to take their beaker tongues really quickly. Go boom, boom. Just turn your wrist, okay? Do a little practice run. And then you're going to submerge the mouth into the ice bath. I think you're ready. Go for it. You can snap it. It's fine. You have about 2 minutes to explain what happened. Not to be officially, I want details. I want the chemistry behind it. 2 minutes to explain the chemistry behind it. All right, guys, come back to your seats with your explanations. You guys can put your soda cans into the recyclables. Don't put your cork back around your. Do not let the cork touch the cup. Okay, leave it unplugged. Leave it plugged in. Make sure it's off. Grab your soda can, put it in the recycle.
Nope, I'll have my next class use it. Oh, you mean of your can? Yeah, of your can.
Yeah, oh, I can have that.
Out of your can. Jordan, do you need shingles now? Okay. You guys can take off your fancy goggles. I've got a lot. Okay. All right, guys, raise your hand if you're feeling pretty confident about your thoughts on how it happened. Matt. Yeah, explain it. What caused it to collapse? So if the cold water was pushing on the can, you're saying it made it collapse. So that means like if I put a balloon in water, the balloon would collapse. Because a balloon's the same thing. The balloon's got air inside of it. Would it cause the balloon to collapse? So that can't be it. So we got something similar but different. Yeah.
We found that like was closer. The water boiling was like adding pressure, and then when it put it in the water, the pressure like exerted
It's exerted into the. Huh?
like the pressure exerted from the can. So like it's not really works.
It sounded better when you. Yeah. But I see where you're going. You're going close, Melanie.
So when you heated the can air inside of the can,
Okay.
and you put it in the cold water, and then probably get all the air inside condensates vapor, so it rushed out really fast. And the pressure outside the can was suddenly higher than the pressure inside the can, so it collapsed.
Okay, so where's the pressure on the outside? Just this air out here? Well, why isn't this air out here crushing us? Okay, we're not selling changing. Can you add to that? Okay, so you're saying the inside air made it collapse on itself. So it pulled the can inward? Am I putting words in your mouth, or is that what you're saying? Okay, I'm going to combine those two. Okay, so here, I want you to draw this picture for yourself. You had this can with air in it, right? There's a little can, that's the mouthpiece there, okay. So it was pushing really hard. The pressure of the gas was pushing very hard on the inside. And outside was pushing on it, but this was a high pressure system inside while we were boiling. And that's what boiling is. It's gases going crazy, bouncing off the inside of the container. And then we dumped it into this cold ice bath. Okay, here's our ice. And this is really cold. Well, if this is really cold and you put the can in there upside down, Melanie said the air rushed out. But it can't because we inverted it, right? So we inverted it, and that's the opening of our can there. The air couldn't really get out. It doesn't really bubble itself out. Because I like the way that you guys said it condensed. So this air inside is just bouncing a little bit now. And it's exerting very little pressure. So it does condense upon itself, so the air rapidly goes from gas back to liquid, or a really cold gas, meaning it just isn't bouncing as much. So it can escape, right? Because generally, if you have two pressures and you allow them to exchange from like the outside air to the inside air, they'll equilibrate, and there's no crushing of cans and crushing of bodies. And because what if you couldn't pop your ears? Your head would explode, or your head would implode. All right, that'd be ugly and horrible and a horrible death. So we equilibrate by popping our ears. Air goes in, air goes out, pressure equilibrates. Well, here it couldn't happen. So it was like, oh no, I can't get my pressure back to what it was. Boom. So what caused it really and truly to go like this? The unbalanced pressure, but who made it implode? The outside pressure or the inside pressure? The outside pressure. The outside pressure is stronger, and it's pushing. It can actually condense and push. Inside pressure doesn't really go, all right, come here and implode. It's the outside pressure of the atmosphere that's pushing on it like this and this and this and this, and it crushes it. It's literally crushing. It's not imploding necessarily, it's crushing. So the outside pressure is so much stronger than what was inside that it caused it to crush. So the P atmosphere is greater than the P gas in the can. And P is just for pressure here. So, kind of cool, huh? So that's all the science behind it. We're going to talk about pressure of the atmosphere a lot more. But what I like to do is kind of run through how to read these diagrams we just were talking about earlier. I got a couple of demonstrations for you tomorrow, mainly because I forgot to go get dry ice today, because I was here before Harris Teeter opened. My bad. Okay, so you guys started writing down some of this, right? Okay, so we talked about the differences mainly between solids, liquids, and gases. What's the fourth state of matter that most people don't talk about? Plasma. Who's ever seen the plasma ball, like at Spencer's? You know the plasma ball? It's actually just energized, ionized gas particles. So it's similar to gas, but it's ionized, so it looks like it has like electricity running through it because it does have some electrical field component to it. So we already know tightly packed particles, defined shape and volume. We already know no motion except for vibrations. You guys tell me, is there an effect on the solid? You have to add pressure to the solid. Yes and no. No, I'm going to start right now. No, I got Bye. Okay, so if you have a solid and you add pressure to it, what happens to it? Great, nothing. Perfect. Increased pressure, no change. Okay, the pressure on a solid is insignificant because the particles are already so close, you can't compress them anymore. They're super, super tight together. So you can't compress it. The only thing that could maybe affect the volume of a solid is something called thermal expansion. And thermal expansion is whenever you heat up something like a metal, for example, and it swells just a hair. And a real experience with that is like if you have a hot motor and you're trying to fix your motor, the I don't know, nuts and bolts and all the stuff that you might need to take off may be different sizes if it's hot or cool, and so you've got to work with the conditions that you have. And sometimes if you were trying to get a hot piece of metal back on a cold structure, it may not fit because it has a thermal expansion ability. So sometimes that happens, but that's very rare. Liquids. Okay, you got some liquid. Add some pressure to the liquid. What happens to the volume of the liquid? Does the liquid decrease a whole lot? Not really, because solids and liquids are similar in the fact that this one's really arranged, an orderly arranged solid. A liquid is pretty close together. It's just not solid. I mean, it's not just a defined shape. It has a defined volume. So the defined volume and defined volume here means that when you add pressure to it, it may not necessarily really affect a whole lot. So increasing the pressure may cause no change. You could put very little change, but it's not very much. It's very insignificant. And again, yes, if solids can do the thermal expansion, liquids can also. So I'm going to put thermal expansion here. Whenever you heat up a liquid, it can expand just a hair. Whereas, think of a liquid that changes density when you change its temperature. Water, right? You cool water down a whole lot. It turns to ice, right? Okay, we've changed the ice. What happened to its density? They go up or down? So ice is more dense than liquid water. Water is the weird one, okay? Water is the one that gets actually less dense when it turns to solid. That's why it floats. Ice gets less dense, so it floats. Okay, so that's something that thermal expansion versus thermal condensing. It can change its density. Now gases, okay, you guys bring your box of air? I didn't tell you. Get your box of air out. You got it? Okay, so there's air particle here, 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 here. Yours might look a little different than mine. Compress it. Okay, you can put some effort into it. You've increased the pressure on the system. What happened to the volume? It got lower. Okay. Expand your gas. Release the pressure. release the pressure. It's calming and collecting now. What happened to the volume? So pressure decreased. What happened to volume? The volume increased. So tell me, is that a direct or an indirect relationship? Well, a direct would be if I increase this, this increases. Indirect, right? So increasing the pressure on a gas, there's a lot of space for compressing to happen. There's lots and lots and lots and lots of space between gas molecules. They're just really, really spread out. They're everywhere. They're here, 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 and here. So you can compress it. So when you increase the pressure, it does decrease the volume, and that's because it's compressible. And vice versa. If you decrease the pressure, the volume will increase because it's compressible and expandable. It can move back and forth, like an accordion. So whenever you're talking about the states of matter, I want you to be able to talk about it can compress or cannot, and the kinetic energy, okay? So, actually, is this kinetic energy? Yeah. So what we have here, kinetic energy, what does kinetic mean? Energy of motion, right? So kinetic energy is energy of motion. Which of these, solid, liquid, or gas, has the highest kinetic energy? Definitely gases. I think this is kind of review. So this is the highest kinetic energy, and the solid would have the lowest kinetic energy because solids are vibrating very little, gases are moving around like crazy. So the kinetic energy is much greater. And so what you can also correlate with kinetic energy is the attractive forces between molecules. Who has the greatest attraction for a neighboring molecule? Solids, liquids, or gases? Say again? Solids, right? This molecule, these are ions, of course, but this ion has a high attraction for this ion versus in this one, and this one, and this one, and this one. So these are all highly attracted to each other. So low kinetic energy should mean that you're not moving a lot. You're like, hey, neighbor, I'll stick here with you. I'm attracted to you. Through London dispersion, dipole-dipole, hydrogen bonding, ionic bonding, all kinds of things can cause that attraction. Gas molecules don't even know they have a neighbor. Okay? It's like way over there, and you can't attract when somebody's so far away. So these are going to have a very low amount of attraction. Simply because they're moving around very quickly, they're less likely to attract a neighbor. Okay, so that's our kind of states of matter deal. Let's look at phases. Oh, this is just a picture. Small vibrations, more vibrations, even more vibrations. And so how am I depicting the vibrations here? These little hash marks around it are motion marks like this, this, and this. So that's sometimes if you have to draw a picture, you can draw with many vibration marks, and that would be, of course, a gas, or a few would be a solid. Okay, so this is the information that's going to be related to thermodynamics and thermochemistry. Thermo parts could always be referencing temperature or heat. And I think all of this is common sense. So I want you to write down what you need to. You have the back of that sheet if you want. You can take it on normal notes. I don't care. But the state of changes are what we're going to kind of focus on first before we get into the phases of matter and graphs. So here are two terms that you are already aware of. Delta H positive, endothermic. Do you remember that? Delta H is enthalpy. And delta H negative is exothermic. Those are two phrases that we've already talked about. And what we're going to do now is we're going to talk about the states of matter that are changing and you tell me, is it an endothermic change or an exothermic change based on the relative energies that are associated with the solid and the liquid, and the solid. So I'm dealing with melting and freezing right now. We all know the change between solid and liquid, or vice versa, is melting or freezing. I'm not reviewing that. Another name, though, that you're going to see is fusion. So fusion means just to melt. You have got to be joking. So, information. Solid versus liquid. Who's got more energy? Solid or liquid? Liquid, okay. So underneath liquid, if you're writing down intense notes here, okay, more energy. So that to me tells me that there's less energy on the solid. Well, how do you get from the solid to the liquid? Do you have to put energy into that process, or do you have to take energy out of that process? Put it in. That's the only way you're going to get from less energy to more energy is to put in energy. So if I'm putting energy in the melting process, I'm going from solid to liquid. Is that endo or exo? Endothermic or exothermic? Endothermic. If you say the word into, put energy in, then it's an endothermic process. Delta H is positive or negative? Positive, right, okay. So this one, guess what? It's just going to be opposite, guys. We have liquid going to solid. Who has more energy? Liquid has more energy. Solid has less energy. So what has to happen? Does energy go into that process to make it happen? Or does energy come out? It's got to come out. Okay, so energy, out with the energy. And so if energy is exiting, it's exothermic. Delta H is negative. So what I'm saying to you is that, let's say I have liquid, and I freeze it. It's freezing, right? It's cold. But energy has exited the system. From the liquid phase to the solid phase, energy has exited. So if you held your hand over top, you put water in little ice cube things, and you put it in the freezer. If you held your hand over the top as the liquid transitioned slowly to solid, you would feel warm as it froze. Isn't that kind of interesting? Yeah? Okay. So what about if I'm going from solid to liquid? That's melting, right? So if you had some ice and it was turning slowly to liquid phase, you would feel, because you're putting energy into that process, so you lack energy, right? Because if you hold your hand over top of that, it's taking energy from you to melt, because you're warm and the ice is cold. It's going to take energy from you, so you would feel cold as the ice melted. It's different. It's about a system and surroundings. So the system being what we're talking about here, you are surrounded because you're not the thing melting. That'd be gross. Okay, so the other component that we relate to this is something called delta H effusion. Well, delta H effusion is what we've started to kind of get familiar with. Enthalpy, meaning delta H, effusion, and we call that delta H flows. Okay, delta H flows means this, energy needed to melt. But it's very specific. It's talking about quantity, meaning 1 mole. And you can kind of see it here. I've got it off the board. But it's the amount of heat needed to melt or freeze 1 mole of substance. That's a definition, but we're going to use it a lot probably later in the unit. So just kind of keep it to the side, put a star by it, the definition, and then we're going to just note the units that are associated with this is kilojoules per 1 mole. So kilojoules is our unit of energy, or joules, but we're going to usually stick with kilojoules for now. Thumbs up when you get here. The next one will go faster because you guys have an idea of what we're doing. We've only done melting and freezing so far. What's coming next? Evaporation and what's the opposite of evaporation? Condensation. Good. Okay. So you guys tell me the first equation up here, liquid to gas. Think about it and tell me if that's endo or exo. James, why do you say this is endo? Okay, so you're going from less energy to more energy, and I'm doing this just for your sake. If you don't want to write down the more and less thing and just you want to think about it, that's fine. But how do you get from less to more? You put energy in. You're putting energy into the process. It's endothermic. So if you held your hand over something that was turning from liquid to gas, energy's going into that process. What does it feel like to you? Say again? Yes, it should feel cold to you because you are not the one melting or evaporating. You're giving energy to the process. You, with your warm body, will give energy to that. Where does that happen in our bodies? Every single day. What's something in or on your body that goes from liquid to gas every single day? I know I'm not the only one that sweats, people. right? Come on. You know that. You have sweat on your skin, okay? It's liquid, right? Well, what happens when your body warms it up? It evaporates. Sweating is your body's natural air conditioning. Sweating is going to cool down your body. Well, how does it cool down your body? It has to take energy from your body to cool it off, right? So how does it take energy from your body to cool it off? Where is it putting that energy that it's trying to get out of your body? Yeah, that's it. Your body heat is this heat. Your body heat is putting energy into the sweat, the liquid, and it's going, okay, liquid, let's go. Let's evaporate. This person's hot and they're going to die. Okay, because if your body gets too hot, you die. So the sweat from liquid to gas, meaning the evaporation process, takes energy from you, so it cools you off as it puts it into the gaseous form. And that's an adaptation that we need to survive. Okay, most of the time we don't really have sweat condensing on us, so we're not going to go into that example. But this one's more energy going to less energy, and so that one's going to be an exothermic process. And so that would be something like, well, you guys tell me, what's maybe a real life example where you have gas going to liquid? Condensing. Huh? On the well, that might be actually deposition. We'll talk about that in a second. But dew forming on like some flowers or grass, you'll have those semi gases going to liquid form. Okay, so let's go to. Oh well, yeah. Let's actually talk about this. Enthalpy of vaporization. That's HVAP. Same exact definition outside of the phase change that's involved here as our last definition. So if you just want to put underneath delta H buzz, the delta H VAP, and just notice that the vaporization is the phase change that's associated. Vaporization or condensation. These numbers, though, that are going to go along with delta H VAP again will be kilojoules per mole. And if we're talking about the vaporization, is that the endo or exothermic process? The vaporization, is that the endothermic process or exothermic process? That was the endo one. Vaporization would be the endo. So this value here would be a positive for that delta H. But if we're talking about delta H condensation, is that the endo or exothermic value? That's the exothermic one. The numbers are exactly the same, kilojoules per mole. Maybe it's like 100 kilojoules per mole, for example. The numbers are the same because they're exactly opposite. It's just opposite is going to indicate the sign is changing, not the number is changing. And we'll really get into that, but I want you right now to know the definition. Okay, so we've talked about boiling. We talked about evaporation, condensation, melting, and freezing. What's left? Sublimation and what's the opposite of sublimation? Where's the D? Deposition. We'll get to that. We'll skip this for now. All right, so solid to liquid is sublimation. That's skipping the liquid phase. Sublimation is going to be skipping the liquid phase, which only happens with certain conditions. Okay, so an example of that would be dry ice, which I will bring tomorrow because I didn't get today. So is that one an endo or exothermic process? Again, it's endo. Why? Okay, so we're going from a low energy state to a high energy state, and that's going to be an endothermic process. So it requires energy to transition states of matter. It requires energy to go from the solid to the gaseous state. Deposition is the opposite of sublimation, and it's going from a high energy gaseous state to a low energy solid state. So does it take energy in or does it release energy? Release is good because it needs to get rid of the excess energy to get back to the low energy state. And releasing energy is an exothermic process. What's an example of gas going straight to solid? Or does anybody have another example of a solid going straight to gas? Did anybody ever put like air freshener in your car? Okay, well, what's the state of matter for that air freshener? It's a solid, and then what do you immediately smell? You smell the gas particles. It's not the solid hitting you in the face, right? It's not the liquid. It's the gas. And that's how your nose smells. It captures the gas molecules and it binds them in the nose receptors. So another example of this would be like an air freshener. An example of the gas going to solid would be like frost on your grass. We talked about dew, which was gas to liquid. Frost forming on plants outside would be an example here. Okay, so those are all your states of matter changes. Now you guys have already described this, so I'm not going to describe this in detail, just a couple of phase transitions. And this is where you guys have that graph. It's not great, it's on the other side of the sheet. It's full dark. I'm going to tell you the labels that are here. So the first one, this is not exactly the same graph, but I'll go with it here. This 1 atmosphere thing, whenever I say something is boiling, what phase transition is that? What two phases of matter? Liquid to gas. So you actually have to go away from the solid. We're not talking about the solid at all. We're talking about the phase transition between liquid and gas at 1 atmosphere. So whenever I say normal boiling point or melting point or whatever, it is regarding 1 atmosphere. And I'll tell you what the equivalencies are. 1 atmosphere, 101.3 kilopascals, and so forth. I'll write that down for you in just a second. But all you do is you look at the pressure, and you scooch over until you see the interface between liquid and gas. So this right here, NBP is normal boiling point. And so what you would do is just drop this down to the lower axis to see what the temperature is regarding on the x-axis. So let's do that for the graph on yours, the phase diagram on yours. Tell me what the normal boiling point is. So look at the 101.3, that's kilopascals, by the way. 100 degrees Celsius, right? So what you're going to do on this one, same situation. Normal boiling point for this substance, whatever this is 100 degrees Celsius. But what substance is this? What boils at 100 degrees Celsius? Water. This is just pure H2O. Okay, so then the normal freezing point is the interface between what and what? What two states of matter? Solid and liquid. So you look at the interface between solid and liquid at the normal pressure, that's here. Well, I have MP here instead of FP. Why? Melting point and freezing point. What's different about them? It just depends on which way you're going, right? What you're starting with. The point is the same. The temperature is the same. So the melting point and the freezing point is the same for this at 0 degrees Celsius. But if I'm going from solid to liquid, I'm melting. Now if I'm going from liquid to solid, I'm freezing. Okay. So you guys tell me, what's on your sheet in front of you? Can you guys answer questions 1 through 6? This sheet right here. Work with the person next to you and try to answer questions 1 through 6. Now try to make this graph. Here's that graph. Here's point A down here. This is point D. This is point B. This is point C. All right, you guys tell me, what does the segment BC represent? What's this to this represent? All the what? All the melting points known to man for this substance. So B to C, I don't have my questions up here. B to C, that segment is all the melting points or freezing points, right? At every different pressure that that substance can undergo, because it's just this transition between solid and liquid. Another way to phrase that is to say solid liquid equilibrium. Solid liquid equilibrium is a phrase I want you to be familiar with. You'll see it on your PS 13 stuff. And that's just what B and C represent, because it's an equilibrium between the solid and liquid phases at every pressure. So using that same logic, can you tell me what A to B represents? Scott? Okay, so the equilibrium of solid and gas. What's another way to phrase that if we're talking about phases of state changes? Right, that's every point of sublimation deposition at these pressures here. And then, Evan, what's the pressure at the normal boiling point? Good. So 1 atmosphere is equal to 101.3 kilopascals. kPa, kilopascals, is what that means. And so what you're saying, that's the same thing saying 1 foot's equal to 12 inches. It's an equivalency, but 1 atmosphere and 1.3 kilopascals are the same. Good. And then what happens to the melting point of the substance as the pressure increases? So here's me on the melting point line. As the pressure is increasing, what happens to the temperature of the melting point? It decreases. So you can you're reading the graph that it's sloping backwards. Sloping backwards means it's decreasing. Decrease in the melting point. Okay, so number 6, I think you guys can see from the graph. Look at, we'll come back to that. You guys have your heat curve out from the notes you took? You drew your heat curve? So what you see here now is I have some labels I want you to add. So on your heat curve, can you please add under your solid to liquid? Okay. Solid to liquid, you see on my graph it says delta H fuzz, delta H diffusion. Did you already have that on your graph? I don't think you did, okay. So that's going to be where we start with that energy required to change 1 mole of a solid to a liquid. So what else do you see that's new for us today? Liquid to gas, right. So the gas liquid line right here is called delta H vap. And that, again, is the energy required to vaporize 1 mole of a liquid. So add those 2 denotions to your graph. But everybody should see that this graph has temperature versus heat added, or temperature versus time. And so what we have here are some state changes and the heating of the matter, but we're going to talk about each of these in just a second. Okay, so what I really need you to be aware of is that the plateaus, or how do you say the plural? Oh, well, it's got an X in it, that's all we know. Okay, so on the flat parts here, what do you notice is not changing? Temperature is not changing. Okay, so this is the big point about these. On the flat parts, plateau, no temperature change. Okay, well, if the temperature is not changing, that's cool, but on the axis in the bottom, it said on some of those heat added. So if heat's being added, why is the temperature not changing? Doesn't heat normally cause temperature change? Yeah or no? Normally heat causes temperature change, but you can absolutely see that after the solid has heated, it just can't add any more heat. It can't change in temperature anymore. So it's changed in temperature to this point. But then once you start to continue to heat it, the temperature's not changing. So what's actually happening now is the solid is starting to get from its nice structured lattice, and it's getting to kind of go free-flowing. So that energy that we're still adding, because this axis down here is sometimes just called energy added or heat added, that energy being added is just going into overcoming intermolecular forces. That is the most important part to know about this. When the temperature is not changing, stuff is still happening. The energy being added is pulling the solid apart so that it's now turning to liquid, but it has to put energy into that pulling apart process. And that pulling apart process I call overcoming intermolecular forces. It's stopping the attractions. So once all the solid has been ripped to pieces, and it's now liquid, it's going to start here at the liquid phase, and it's going to heat up, heat up, heat up. Temperature's changing. The liquid's getting hot. And it's like, I can't be a liquid anymore. What's it going to start to do? Rip it apart. Hold on, right? Rip it apart into from its liquid to liquid kind of attractions into gases, and it's going to start to overcome more intermolecular forces here as it continues to rip the liquid attractions apart. And then eventually all that liquid is now turned to vapor or gas. And that vapor can then turn on and heat up even more. So during the no temperature change, we call that, first of all, a phase change. And a phase change that's occurring means that they're overcoming intermolecular forces so that phase can change. So this phase change is called what? From solid to liquid? Solid to liquid? Melting. Okay, this one's called melting. And this one's going to be called vaporization. So the phase changes occur on the plateaus, and the heating up parts occur on the slants. And during the phase changes, it's just the energy added is overcoming intermolecular forces, is not adding to the temperature whatsoever. Okay. So I'm going to stop right now. You guys have about 17 minutes to practice on some of these graphs. Got that heat curves and cool curves for you. These are yours. Okay, write on them. I want you guys to start on. I can't separate this. That. I want you guys to start on section 3 and 4, and then come back to section 2, and then go back to section 1. So we just go backwards. Let's go from 4 to 1. Sections 4 to 1. On the phase change side, the other side has some gas stuff on it. We haven't even touched that yet. We won't for probably a day. So start on this side. I'm sorry, I didn't label it. Start on section 3. I was thinking the one below it was section 4, but start on section 3, which is the right-hand side of the paper, and then move back. If you want to start for a minute, that's good. Talk to the person next to you. You can call me over as needed. Got it, Alina? Guys, you're gonna have to draw your own normal line. I drew the normal line on this one for you at 101.3, which is 1 atmosphere. When it says normal, boiling point, freezing point, extinction point, I don't know. If it says normal, it means at what pressure? It means at 1 atmosphere. So you're gonna have to draw your own. I drew it on all the ones here, but you guys have a fresh graph now. You need to draw normal before you can figure out the normal boiling point or the normal freezing point. We're gonna go.
Water going from ice
So it says creating graphs.
That section, yeah, the one that's called section 1.
Miss Emma,
Yes.
when the bell rings, could you send Eli Tugboard to the attendance office for dismissal?
Thank you.
Thank you.
As we still have like 5 minutes, you're good. I will pop up the section 3 answers because I think some of you guys had a hard time reading that graph. But you should be able to back up all the way back to section 1. Yeah, it took us about an hour.
So raise your hand if you need some help proceeding, but I think that you use your notes in your reading guide. You're good with the heat curve. The drawing from number 1, you can just put a lot of paper. Oh, you see the action. Somehow I thought we were going to do another lab and a benchmark today. So sorry that you were rushed here at the end, but yeah, I saw a lot of you guys got a good jump on PS13. How has it been so far? It's not a lot of problem solving. It's more like reading and looking back at your reading guide, looking through the book some. It's more multiple choice than you've ever had on a problem set before. So here's what it looks like. Finish PS 13. There you go. So now I can look at lunch. Okay. There's nobody else. There's nobody else. It's just you. I'll take it up in your portfolio stuff. A little loud.
I do think that's Do you want me to walk around?
You're a cripple. No. You're good. Cripple has privileges.
Okay, cool.